Welcome back, everyone, to the final session of the second virtual workshop on double categories. It's great to have you all here. Today we'll have two talks, and the first talk will be by Dylan McDermott, who will tell us about formal theories of presheaves and cocompletions. So please take it away.
Hey, thanks for the introduction, Bryce. So this talk is about presheaves and cocompletions, although I will warn you now that this will be mostly about cocompletions. I view kind of cocompletions as the goal of this work, really, but presheaves are kind of very closely related, so I will have to talk about presheaves later on. But most of this will be about cocompletions. So I'll start with a few examples of, well, cocompletions kind of in the case of ordinary categories, or maybe enriched categories. It works fine for enriched too. I don't know how many of these you will have seen, but probably you've seen a lot of them. So for example, if you take a small category A and we freely add small colimits to it, then we get the category of presheaves on A. Right, this is kind of a well-known fact. So in some sense, presheaves on A is the free category with small colimits over A. Or in other words, it's the small cocompletion of A. But there's a bunch of other examples of this kind of thing. So for example, if we take the category of finite sets and we add filtered colimits instead of all colimits, then we'll just get the category of sets. And I can generalize this example. So I can say, well, if I replace finset with just any small category with finite limits, and then I add filtered colimits to this, then I'll get a locally finitely presentable category. And it turns out that every locally finitely presentable category arises in this way. So there's a bunch of other examples of this, and you can replace, filtered colimits with other classes of colimits, like sifted colimits, or maybe absolute colimits. But there are various kind of categories which arise naturally by just adding colimits to some existing category. So let me say a bit more formally what this really means. So I'm going to assume that we have some class of small categories, psi, and these are going to be the shapes of the colimits that we're going to take. So I'm going to be considering colimits of shape I, where I is some category from psi. And of course, we can say, well, the category is phi cocomplete if it has all colimits of these shapes. And the functor is phi cocontinuous if it preserves all of these colimits. Now we can say what a phi cocompletion is. A phi cocompletion is first a functor from this A that we start with into some other category, such that this other category has phi colimits, so it's phi cocomplete. And also for every functor from A into some other phi cocomplete category, we can extend this functor to a functor from phi of A into X. And this extension has to be unique with the property that it's firstly phi cocontinuous, it preserves these colimits, and also if we compose with this functor phi, we get back F. So this is some universal property that describes what this category phi of A is, right? It's some universal property that talks about functors from phi of A. So in particular, we can specialize this definition. For example, we say phi is all filtered categories, then we get a definition of filtered cocompletion. The filtered cocompletion of A is essentially what we get by freely adding filtered colimits to A. So if you just specialize what I had in the previous slide, we say, well, this category has filtered colimits, and then there's some universal property that talks about finitary functors, so the functors that preserve filtered colimits. So for example, if A is finite sets, we can take the filtered cocompletion of this, and we get sets. We get the category of sets. And this functor will just be some inclusion. Just the inclusion of finite sets in sets. Okay, so these things are kind of well known, and there's a lot of theory about these, in particular in the case of enriched categories. So if we say that V is an SMCC, a symmetric monoidal closed category, and we assume that it's complete and cocomplete, then we can prove lots of things about these cocompletions. So in particular, there's this one paper here, which I quite like, and this has a lot of the theory of these cocompletions. In particular, it talks about how we can construct these things, and then goes on to prove lots of results about these things. So today I want to talk about formal category theory, right? And what I really want to talk about is what happens, is how we can formulate this kind of definition in the setting of formal category theory. So this means I want to somehow generalize from V categories to some other class of category-like structures. In particular, a particular motivation of mine is to drop this condition that the monoidal category has to be symmetric, which is actually quite a non-trivial thing to do. Because there are actually cases of monoidal categories that I want to enrich in which are not symmetric. So I kind of want to drop this condition that we have symmetry. But we can also imagine that we maybe want to do cocompletions of internal categories or some other kind of collection of category-like structures. Okay. So I'm doing formal category theory. So I'm going to assume some setting in which these category-like structures exist. And the setting we're going to work with is virtual double categories. I assume that a lot of the audience is familiar with these already. But I think it's probably good to just kind of fix some terminology and fix some notation. So firstly, a virtual double category is very much like a double category, right? So we have some kind of objects, some kind of type cells, which will be the vertical things, the things I'll write vertically, some kind of loose cells, which I'll write horizontally, and also two cells. But the main difference from a double category is that we don't require these loose cells to be composable. So we can't just take a loose cell from Z to Y and a loose cell from Y to X and compose them. And as a consequence of this, I'll need to talk about two cells which have kind of chains of loose cells in the domain, rather than just a single loose cell in the domain. But otherwise, virtual double categories look much like double categories. And the only example I'm going to give you in this talk is V categories, where V is some monoidal category. So here the objects are V categories, the type cells are the V functors, the loose cells are the V distributors or V profunctors or whatever you want to call them. And a two cell of this shape is kind of is essentially a natural transformation, kind of generalized natural transformation. So here you can see these distributors P1 through Pn are in the domain, and Q along with F and G are in the codomain. So if you've seen the double category of enriched categories before, you've seen essentially this definition. I'll just note at this point that I'm really only assuming that V is monoidal here, nothing else. So in particular, we won't be able to compose loose cells in general, and this will be true throughout this talk. In fact, even if we assume that V is, say, complete and cocomplete, we can't compose these loose cells, because in general, I'm going to consider large V categories, and composition of loose cells would generally be given by some coend, which would have to be a large coend. And I can't assume these exist in general. So this is why I'm considering a virtual double category rather than saying double category. Okay. So I hope everyone is fine with this kind of structure. I'll need to add a few more things to this because I actually want to talk about virtual equipment. So a virtual equipment has loose identities, so identity loose cells. We can say what this is an arbitrary double category. It's a loose cell, or for every object E, we have a loose cell from E to itself. And this comes with some two cell of this shape, satisfying some universal property, which talks about having loose identities in the domains of two cells. So in particular, in the case of VCAT, we do have a V distributor from every E to itself, and this is just given by the home objects of E. Then the other bit of structure we'll need is restrictions. So this is where we say, well, if we have a loose cell from Y to X, and also a couple of type cells, so one into Y and one into X, then we can restrict the loose cell along these type cells, and then we'll get some other loose cell from Y prime to X prime. And again, this will have some kind of universal two cell. So some two cell which has some universal property. These are quite simple. In the case of VCAT, it's just we take some distributor P and we compose with these functors f and g. Okay, so throughout this talk, I'm going to assume we have a virtual equipment, which means I'm going to assume we have all of this structure. So in particular, the special cases of this structure, we can take a loose identity on E and restrict it along some f and g. And this I'll just write as EFG, so I'll just kind of ignore this 1, 1. And as a special case of this, we have companions and conjoints for every type cell. And these will be the companions and conjoints in the sense that they have some universal property that you kind of expect. Okay. And then just one kind of final comment about restrictions. It's not going to be so important for cocompletions, but it will be important for presheaves. But I'm going to assume that we choose restrictions for every P and F and G. So we choose a Cartesian cell like this. And I'm also going to assume that these restrictions are strict, which means if we restrict along identities, we get P back up to equality. And if we restrict twice, then we get just a restriction of composite, again, up to equality. So it doesn't matter too much yet, but it will kind of matter when I talk about presheaves, because these will involve a slightly strict definition. Okay. And then kind of final comment about virtual equipment. Because we have restrictions rather, whenever we have a two cell like this, we can effectively represent it by a two cell like this. Right? The universal property of the restriction says we can move this F and G down and restrict Q to get a two cell of this shape. And two cells of this shape are in bijection with two cells of this shape. So it turns out that, in general, we really only need to consider two cells where the type cells are identities. Right? Whenever we have a two cell like this, whenever we have a two cell 5 like this, we just replace it with one of these sides. So in the case where I have a two cell where the type cells are identities, then I'll just write it linearly like this. Right? I'll say psi goes from P to QFG. And in fact, for the rest of this talk, I will only consider these globular two cells. I won't actually need to draw any kind of squares like this anymore. I'll just consider only the globular ones. Okay. So I want to talk about cocompletions, right? So I'll just remind you of the definition kind of in CAT. It involves a bunch of terms I would need to define in an arbitrary virtual equipment. Right, so for example, I'm talking about colimits in a virtual equipment, colimits in an object of a virtual equipment, and then want to talk about when a type cell preserves some colimits, for example. So I'll need to say how to define colimits in a virtual equipment. The definition looks like this. So firstly, we need kind of another kind of universal structure in a virtual equipment. So this is a kind of closed structure for loose cells. So I want to say if I have a loose cell from X to A and a loose cell from Y to A, then often, it won't always exist, but often I can take a right lift of Q through P. And that's a loose cell from Y to X. And this loose cell satisfies some particular universal property. So if you've seen, for example, closed multi-categories, you've seen exactly this universal property before. It just says, as soon as I have a right lift on the right-hand side of a two cell, on the codomain of a two cell, then I can move this P to the left-hand side of the two cell. Okay, so you might want to know what role this plays in the case of VCAT. So in the case of VCAT, we can say exactly what these right lifts are. So here I have now distributors P and Q. Then if I fix some X and Y, I get two presheaves on A, using the kind of contravariant structure of P and Q. And now I can talk about natural transformation, V natural transformations from between these two presheaves. And in fact, I'll get some object of V, the kind of object of V natural transformations from this P blank X to Q blank Y. So this is something that I can define using a universal property. I can say, yeah, this object is just some object of V which carries some extra structure satisfying the universal property. And if you've done much enriched categories before, you will have seen basically this thing. So in the case where, in particular, when V is closed, we can always write this using the closed structure of V and an end over A. So the kind of usual end formula for natural transformations. Now, these things don't always exist. I'm not going to assume that right lifts always exist in my virtual equivalent X. I'm just going to assume that some particular right lifts kind of exist occasionally. Okay, so now I know what right lifts are, I can talk about weighted colimits. So the first thing to say is that here I'm talking about colimits weighted by a loose cell. If you've done much enriched categories, you will have seen kind of colimits weighted by a presheave. I think it's a bit rarer to consider weighted by a distributor, but we can talk about these just as well. So I can say if I have a loose cell from X to A and a tight cell from A to Y, I can talk about the colimit of F weighted by P. This will be some colimit in Y. And it will in fact be a tight cell from X to Y satisfying some universal property. And the universal property actually just says what the conjoint of this tight cell is in terms of a right lift. So one way to say this is it says something like, this is how we map out of this colimit. Right? The maps out of the colimit are given by some right lift. And if you expand out what this means for enriched categories, in particular using this kind of formula for right lifts, you will get the kind of thing that you would expect for a colimit in an enriched category if you've seen this before. Okay, so we have some notion of kind of colimits in virtual equivalents. I'll just give you one particular instance of this before I move on. So in particular, we can talk about can extensions as colimits. So if I say I have some type cell J from A to E, and also some type cell F from A to Y, then I want to take the can extension of F through J. So this will be some type cell from E to Y, and it will be given by a colimit. In particular, the kind of universal property of this left extension just says, well, in fact, this left extension is the colimit of F weighted by the conjoint of J. So because I formulated this in terms of colimits, this is in particular a kind of point-wise notion of can extension. Right? So it's stronger than the universal property you would expect from like a can extension in a two category. It's really the thing that I want to talk about here. I need this stronger notion, point-wise left extension. And again, you can kind of expand out what this means for enriched categories. So this colimit says we have some universal property that says how to map out of a can extension. And it says something like, to give a map out of a can extension, we need to give some kind of phi natural transformation. So again, if you've seen enough enriched category stuff, you will have seen exactly this formula before. Right? This is the usual definition of point-wise left extension for enriched categories. And I'll just note at this point, I'll generally just say left extension and kind of drop the point-wise on the can part. It's just easier to say left extension, but I will always mean kind of the point-wise version. Okay, so now I think I've given you enough stuff to say what to begin kind of giving the definition of cocompletion in a virtual equivalent. So I'll just remind you, in the case of cocompletions in CAT, we have some definition that talks about cocomplete objects and cocontinuous functors. So now we can generalize this to virtual equivalents. We can say, well, now my phi should be a class of loose cells. So these loose cells are the weights which I'm going to use inside colimits. I'm going to talk about colimits weighted by p, where p is some element of psi, of phi rather. And now I'll say, well, an object E is phi cocomplete if it admits all of these colimits. I've told you what a colimit is, so you know what admits one of these colimits means. And I'll also say that a tight cell is phi co-continuous if it preserves all of these colimits. I haven't really said what preservation means, but if you think about this for 5 minutes, you'll kind of come up with the right definition. It would just say something like, G of a colimit is actually a colimit. Okay, so now I can just kind of write down exactly the definition that I had for cat, but in the case of a virtual equipment. Right, so I can say what a phi cocompletion of an object A is. It's now a tight cell into some other objects. Subject to 2 requirements. The first one is that this other object is phi cocomplete. And the second one is that for every tight cell into a phi cocomplete object, we can extend this tight cell to some phi co-continuous tight cell from the cocompletion. And this is unique such that composition with this tight cell phi gives you back F. Right, so it's exactly the definition that I have for cats. It's just now generalized to the case of a virtual equipment. But you've probably noticed that at the top of the slide, I'm claiming this definition is wrong. And the reason I think this is wrong is that it's just far too weak to prove very much about. So I mentioned earlier that there's a bunch of results about cocompletions for V categories. I can prove things like, for example, these tight cells are always fully faithful, right? In the case of V categories. This turns out not to be the case for a virtual equipment. So if I just take this definition, then there's nothing that guarantees this tight cell phi is actually fully faithful. And there are various other things in the theory of cocompletions that we might hope to be true, but which really aren't if I just take this as the definition. And what happens is, well, you can say in the case of V categories, I actually know how to construct cocompletions. You kind of take some kind of presheave category, or you take a full subcategory of this, and then you do some stuff. And actually, it follows from the construction that we can prove various results about cocompletions. But these results don't really follow from this definition as such. They follow from the construction. So this definition doesn't really seem to capture what's really happening in these constructions. So the question is, what is missing from this? So I'm going to keep 1 and 2. This I will keep as part of my definition, but I'm going to add some more stuff. The first thing to notice is that I haven't really said much about loose cells involving this phi of A. Right? I've said something about tight cells whose domains are phi of A, but I haven't really said anything about loose cells involving phi of A. So the next thing I want to add is some kind of condition that says how these loose cells behave. And in fact, we can take this second condition and kind of write out a version of it for loose cells instead of tight cells. So we can say, well, given any loose cell into A, whose codomain is A, we can require that this can be extended essentially uniquely to another loose cell whose codomain is the cocompletion. And this is essentially unique such that the loose cell is phi co-continuous in some particular sense, and such that restriction along this phi A actually gives us back P. And here I need to say what phi co-continuous means for a loose cell. It's kind of analogous to what it means for a tight cell if you kind of squint enough. But one way to see this is if I take this Q here to be the loose identity, this will be exactly the universal property of a colimit. This is what I gave as the definition of colimit. But here I'm just saying this isomorphism also holds if we take Q to be some other loose cell. That's what I mean by saying Q is phi co-continuous. And maybe you're wondering how this 3 really relates to 2. If you take here P to be the conjoint of F, then you'll get some loose cell, P tilde, and this will turn out to be the conjoint of this F tilde. Right, so if I just take this condition 2 and just replace everything with conjoints, and then generalize to arbitrary loose cells, I get kind of this condition. I think I'll just mention one more thing about this condition, which is that here I'm not requiring X to be phi cocomplete. And this turns out to be quite important for some of the proofs. So here in condition 2, X was phi cocomplete, and I had to require this because otherwise we can't really take, and we can't really extend a type cell. We need to extend a type cell, we have to construct something in X. This will be given by colimits in X. So we can't do this unless we assume some colimits in X. But in the case of a loose cell, this is actually fine. We can usually extend loose cells to loose cells like this because we're not constructing anything in X by doing this. We're constructing something in, for example, V, we're taking V categories. Okay. And then there's one more condition that I need to add, which says something a bit more about what this P tilde is. So I'm going to require that this P tilde is actually a right lift. And it's a right lift through the conjoint of this phi A. I'll need this condition to say something about what the two cells in virtual equipment look like when these two cells involve kind of cocompletions. And I'll give an example of this of using this condition on the next slide. So the fourth condition is essentially just this P tilde is some particular right lift. There's also some extra little thing that says some canonical two cell is actually an isomorphism. That's because in some of these proofs, we really need to deal with some canonical two cells rather than just arbitrary like isomorphisms. So we do have this like little extra condition about canonical two cells. But you can kind of ignore this condition for the talk. Okay, so I claimed earlier that we couldn't prove phi A was fully faithful just from this 1 and 2. But I want to claim now that this is really my definition of phi cocompletion. And in particular that I can prove from these conditions that phi A is now fully faithful. So firstly, I'll just tell you what fully faithful actually means in a virtual equipment. It's not such a complicated definition. The definition says, if I take a loose identity, take this loose identity and restrict along my type cell, then I should get a loose identity back. That's what it means for this type cell to be fully faithful. In the case of ordinary categories, this says essentially the action of morphisms going from left to right is a bijection. Right, it's the usual definition. Okay, so supposing that this phi A is a cocompletion, how do I prove that phi A is fully faithful? Well, the first thing to note is that it's enough to have bijections like this between two cells, which are natural in P. As soon as I have this, then these two cells in the domains, these will turn out to be isomorphic. Okay, and how do I know that there are bijections between two cells like this? Well, to show this, it's actually enough to show that two right lifts are isomorphic. In particular, this right lift of P through loose identity is isomorphic to the right lift of P through this other loose cell. Because if these right lifts are the same, then I can just prove this bijection as a consequence of that. Okay, so now I'm claiming that these two right lifts, well, they both exist and they're in bijection. Oh, there's an isomorphism between them. How do I know this? Well, firstly, I know what a right lift through a loose identity is. These are kind of trivial. You can prove easily that taking a right lift through a loose identity does nothing. So this bottom right lift is actually just P. And then, well, condition 3 on the previous slide said that P is the same as the restriction of P tilde along phi. But what is P tilde? Well, the condition 4 on the previous slide said this P tilde is actually some particular right lift, right? This right lift here. And then there's some little riddle about how a restriction of a right lift is also, again, a right lift. So I can push this restriction into the right lift and I get this. Right, so then I have my isomorphism. And this is enough now to prove that this phi A is fully faithful. But I'll just note that I used both 3 and 4 here. So actually, in particular, it turns out this condition that this canonical two cell being an isomorphism, it turns out this condition, assuming all the rest of it, this is equivalent to phi being fully faithful. There are various kind of equivalent definitions. Okay, so I can begin to prove some nice things about these cocompletions that really rely on these extra conditions. And I'll also note at this point that all the cocompletions, for example, in enriched categories, do satisfy these conditions. Right? You can prove this again by just taking the construction of a cocompletion in an enriched category and just verifying these conditions hold. That's actually not so difficult. Okay. So I will want to prove some more kind of facts about cocompletions in virtual equipment. For the next fact I want to prove, I'll need to kind of add some more definitions about virtual equipments in general. The next definition I'm going to give is that of a composite of loose cells. Right, so composites, as I said before, they don't in general exist. But we can say, well, if a composite exists, then it will be satisfy some particular universal property. So we can define what it means to be a composite of Q and P by saying, well, there is some 2-cell which gives you some universal property. And this just says, you know, you can replace this O dot with a comma on the left of the 2-cell. These are the usual composites you would expect in a double category. So, you know, in the case of VCAT, the composite will be exactly the kind of co-end of, you know, some tensor product, the kind of formula you would expect to write down. But it actually turns out that composites aren't quite the right thing for what I want to talk about. And we'll need to consider kind of a weaker version of this universal property. So I'm calling a left composite. So it's exactly the same universal property, except I can only apply this universal property when there are no kind of R primes to the left of the composite. Right, so I only get the special case where m is equal to 0. And I'm not convinced there were many kind of left composites which are not actual composites, kind of in real virtual equipment. But the reason I'm talking about left composites here is that for various things that will come kind of in the rest of this talk, I can prove that I have left composites, but I cannot prove that I have composites. Right? So I really need to consider this weaker definition. Okay, and then the next definition I'll give you is that I have an absolute colimit, or rather a J absolute colimit. Maybe you've seen kind of absolute colimits in ordinary categories where you say a colimit is absolute when it's preserved by every functor. This is kind of a generalization of this definition. So if I have some type cell J from A to E, and I have some colimit in E, I can talk about when this colimit is J absolute. And the condition is that this particular kind of restriction of a loose identity is actually given by a left composite, or actually satisfies the universal property of this left composite. Maybe one way of seeing this is in the case of ordinary categories. This is essentially saying, well, as soon as I have a morphism from some Jx to a colimit, to this J absolute colimit, then I can factor this morphism through some f of y. And especially if you're seeing, you know, the kind of definition of like a finitely presentable object in terms of like factoring morphisms into colimits, then you've seen this kind of thing before. But I think the main thing I want to say about this definition is that if a colimit is J absolute, then it's preserved by every left extension along J. So in particular, if J is the identity, well, every type cell is a left extension along an identity. So this says, well, this colimit is preserved by every type cell. So in the case where J is the identity, I kind of recover the ordinary definition of absolute colimit. And in fact, this sentence almost has a converse in the sense that if I kind of assume enough stuff exists in my virtual equipment, then I can prove that whenever a colimit is preserved by every left extension along J, then that colimit will be J absolute. So this statement is almost an equivalence, but I need to assume that a bunch of left extensions exist to kind of prove it. So for example, in the case where we take ordinary categories and A is small, this is always the case. So J absolute is equivalent to being preserved by left extensions along J. Okay, why have I talked about this definition? Well, I want to talk about this definition because it comes up quite a lot when you talk about cocompletions. In particular for this reason. So if I take a cocompletion, a phi cocompletion, then this object will have phi colimits. And it turns out these colimits are also always phi absolute, where phi is this fully faithful type cell. Perhaps I won't go through the proof. I don't think I have time for this, but I'll just kind of mention a couple of points, which are so here I'm just saying, well, I need to prove the universal property of this left composite. This is essentially what I'm doing. So I'm showing there is some bijection between two cells. And here, because this loose cell appears on the left, I can move it to the right by taking a right lift. Right, and this is only because it appears on the left. If I had a bunch of R primes to the left of this, I wouldn't be able to do this. So this is why I'm considering left composites, right? Because I really need this to appear on the left. Then the other thing to mention is that once I move this to the right, I have one of these right lifts, like the right lifts through the conjoint of phi. And I told you as part of the definition of cocompletion that these have some kind of nice properties. So in particular, they preserve phi colimits. And that is this step in the proof, and this is kind of the essential reason why phi colimits are phi absolute. Because I required these loose cells in particular to be phi cocontinuous. Okay, but I won't go through the proof in any detail. The main kind of facts I want to use this for is the fact that if I have a type cell from a cocompletion, it will turn out that preserving phi colimits, so being phi cocontinuous, is actually the same as being a left extension along this phi A. And the reason for this involves absolute colimits. So, for example, to prove 2 implies 3, well, I told you before that these left extensions preserve these absolute colimits, right? So 2 implies 3 kind of easily. And 3 implies 1. Why is that? Because that is because phi colimits are phi absolute. And the fact that 1 implies 2 kind of again uses this uses the definition of cocompletion. So perhaps you know special cases of this fact. So for example, in the case where we take a filtered cocompletion, then to have a finitary functor from a filtered cocompletion, well, that's the same as this functor being a left extension along the filtered cocompletion. So for example, a finitary functor from set to another category is the same thing as a left extension along the inclusion of finite sets in set. This arises as a special case of this kind of fact. And I'll also just note that here I'm not assuming that X has phi colimits in general, right? This applies even if X does not in general have phi colimits. This kind of follows from, this kind of happens because earlier when I was talking about loose cells, I didn't require X to have phi colimits. I just said an arbitrary loose cell. This is kind of the reason why we don't need X to have phi colimits. Okay. So now at this point, I will actually get to talk about presheaves. But first, I'll tell you why I want to talk about presheaves. So the reason I want to talk about presheaves is usually, for example, in the case of enriched categories, the construction that you use to show that a cocompletion exists is you essentially say something like, well, start with a presheave category, take a full subcategory of that, some particular thing, and then this will turn out to be my cocompletion. So the idea is that somehow I want to show that if enough presheaves exist in my virtual equipment, or rather presheave objects, then I should be able to show that a cocompletion exists by doing essentially the same construction. Okay, so what is a presheave object? Well, the definition looks like this. Essentially, all I'm saying here is that every loose cell from Y into A can be represented as a type cell from Y into presheaves on A. So in fact, in particular, in the case where you take enriched categories for a symmetric V, you can define a distributor as being like a V functor into presheaves. This is one of the common definitions. So it essentially encodes this fact that you can represent loose cells by tight cells. But precisely the way I'm going to formulate this is I'm going to say, well, there is some particular loose cell from presheaves to A. In the case of enriched categories, this is just like take your presheaf and apply it to A. And kind of by restricting this, this loose cell pi, I'm going to get all of the loose cells whose codomains are A. So this part of the definition. But then again, I'll need to say something about how the two cells work. The easiest way to say this is to say that pi is dense in the sense that the right lift pi through itself is the loose identity. I'll show you now why I'm requiring this. So the first thing to say is that if I restrict the loose identity on presheaves, then I'll get a right lift. Right. It's a bit of effort to prove, but you can prove this. So in particular, if I have two loose cells whose codomains are A, then I can always show that the right lift exists. Because it will be given by this kind of form object. And this shouldn't be too surprising at this point because I kind of, well, I already wrote out this formula kind of for V natural transformations before, this kind of end formula. And yeah, the Hom objects and these presheaf objects in the case of V categories are given by this end formula. So it shouldn't be too surprising that if I take this restriction, I'll just get a right lift, because I said earlier that this was a right lift. And the other thing to note is that we can prove some kind of Yoneda lemma. So firstly, there will always be a tight cell from A to presheaf on A. This is kind of the tight cell that corresponds to the loose identity on A. And by using this fact about right lifts, I can prove that if we take the restriction that goes from Yoneda to some Q, then I'll just get Q back. So this is kind of some encoding of the Yoneda lemma. Okay. Now I don't want to talk about kind of, I want to kind of slightly generalize this definition. Because earlier I was considering kind of classes of loose cells, and I want to generalize this to classes of loose cells too. So here I'll say, well, if I have a class of loose cells phi, then I'll talk about the phi presheaf objects for A. And the definition is exactly the same, except here I want a bijection between loose cells Q from phi and the tight cells into the presheaf objects. And so I'm saying, a tight cell whose codomain is the presheaf object is the same thing essentially as a loose cell from phi. So the definition is just the same as the previous slide. I'm just saying, I've just added the fact that Q has to be in phi here, and also this condition that if I restrict this pi along a tight cell, then I will again get something in phi. This guarantees I have a bijection involving things from phi. And again, we get the kind of same facts about right lifts and some Yoneda lemma, where now the Yoneda lemma assumes that kind of this loose identity is in phi, because otherwise I can't represent this better. Okay. So now my claim is that I can construct phi cocompletion, assuming some conditions, using a presheaf object. So the main thing that I need to do in order to kind of show that this is true, so I need to show that presheaf objects will often have colimits, right? Let's get this part. So I want to ask, well, what is a colimit in a presheaf category? Or in a presheaf object, rather. So here I have a tight cell whose codomain is the presheaf object, and also some loose cell, which is the weight of the colimit. Now the colimit should be a tight cell into this presheaf object. That's what the definition says. But this is good because I know what tight cells into the presheaf objects are. Right? They correspond to loose cells from phi. So to show that a colimit exists, I just need to show that there is some loose cell inside phi, which has the required universal property. And it turns out this the kind of correct loose cell to take is the left composite of Q with the loose cell corresponding to this F. Right, it takes some effort to prove this, but it will turn out that this has the correct universal property for the colimit. And it also turns out, by the way, that this colimit will always be absolute with respect to this kind of Uneda embedding phi. As long as this Uneda embedding exists, so as long as I have the correct loose identity inside phi. Okay. So it is the case that presheaf objects usually have colimits. In particular, if I take the case where phi is all the loose cells, and I assume all the left composites exist, and I'll get that all colimits exist in this presheaf object. Okay. So this does not quite guarantee that this presheaf object is a cocompletion. I'll need to add some more conditions to guarantee this. But we're kind of almost there at this point. So supposing I want to take the cocompletion of some, with respect to some class of loose cells phi. Okay, well, how do I do this? Well, I want to say that this cocompletion is the presheaf object on phi in some cases. Okay, so what do I need for this to be true? Well, firstly, I need the presheaf object to exist. I will also need some embedding, so some map that goes from A to phi of A, right? And this will be this type cell corresponding to the loose identity. And for this to be the case, of course, I need the loose identity to be in phi. Then I'll also want this presheaf object to have a bunch of colimits, and for this, I'll just assume that this phi is closed on the left composite. Right, so the colimits will be given by left composites. And then the kind of final condition, kind of slightly subtle one, I guess, is that I require a bunch of right lifts to exist. So that in particular says I can take right lifts through the conjoint of this phi A, which are kind of required in the definition of cocompletion. But in particular, but actually for a cocompletion, it turns out that whenever this P is in phi, I can always take right lifts through P. And that's not in general quite the case for a presheaf object, because I can only, for a presheaf object, or rather a presheaf object only guarantees I can take right lifts of Q when Q is in phi. But here I really need to require this exists for every Q, for every loose cell Q. But under these conditions, it will turn out that the phi cocompletion of A is actually given by this embedding into the presheaf object. Right, so I'm not giving you the proof in this talk because I think I don't really have time. But it turns out under these conditions, I do get a phi cocompletion. This is not quite the result that I want, because usually when I start with some phi, like I say, maybe phi is filtered categories, for example, usually the cocompletion is not given by the presheaf objects for this phi. And the problem with this is, well, like usually, for example, phi will not be closed in the left composite. And maybe phi doesn't contain the loose identity. So actually, I can prove a slightly better result than this, which says, well, supposing I want to take psi cocompletion for some class psi. Well, this will be given by a presheaf object for some phi. As soon as, well, firstly, all of these conditions hold that guarantee that this presheaf object is a cocompletion. And also that phi and psi turn out to be colimit equivalent. I haven't said exactly what this means, but it essentially means having phi colimits is equivalent to having psi colimits, and preserving phi colimits is equivalent to preserving psi colimits, and so on. So then it will turn out to be the case that, well, the phi cocompletion is given by the presheaf object, and the phi cocompletion is equivalently the psi cocompletion, because these are colimit equivalent. So now the psi cocompletion of A is given by this presheaf object on phi. And we can kind of use this to kind of model the standard construction that you'd use for enriched categories, because there you would say something like, well, this class of presheaves I'm going to take is just given by saying, well, I'll take the smallest class of presheaves that contains representables and also closed under these colimits. These conditions essentially say that And these presheaves are closed under loose identities and under the left composites in the kind of virtual equipment world. So the thing that I had on the previous slide essentially says, well, I can take my phi to just be the kind of closure of psi under left composites and under the loose identities, and then I'll get kind of this kind of something that matches this construction. Okay, that's all I really wanted to say today. We have a bunch more kind of results about kind of cocompletions and presheaves and how they relate to things like relative monad and so on. I don't think I really have time to talk about these now. But I'll just say that we are currently preparing a draft of a paper. Hopefully we'll have it on archive sometime soon. It's kind of when me and Nathaniel get around to actually finishing this, it's mostly finished at this point. There's just kind of little details to fill in. So yeah, hopefully we'll have a paper on archive soon that people can look at. But other than this, I'll kind of stop here and find out if you have any questions.
Okay, thank you very much. We see lots of clapping of hands. Participants are able to unmute yourself. So if you'd like to ask a question, please just go ahead or raise your hand first and then ask. But
I just had a quick question about this colimit equivalent
Yes.
definition that you just glossed over with psi and phi. You mentioned two things. It was surprising to me that these things are different. So maybe you have like an easy counterexample that even if psi and phi colimits, like having one is equivalent to having the other, it doesn't mean that preserving one is equivalent to preserving the other. Is that like a correct summary of what you said the definition is? Like, are those two...
So the definition, I can say in more detail. The definition says having phi colimits is the same as having psi colimits, and being phi cocontinuous is the same as being psi cocontinuous, both for tight cells and for loose cells. That's a good question, actually. I don't think I know of an example off the top of my head. Yeah, I would need to think about this. I think
Okay.
I certainly don't see any way to prove that being phi co-continuous is equivalent to being psi co-continuous.
No, but it just surprises me that it wouldn't be true. But yeah, I don't know. Maybe finding an example's hard. But yeah, I was just wondering if you had one. But that's
no,
fine.
not off the top of my head.
Okay,
Maybe
that's cool. But that's good because I couldn't think of one, so I'm glad to hear that it's hard to think of one. Okay, thanks.
perhaps the silly question that I had, if you have a virtual double category and it has all loose identities and composites, then it's a double category.
Yes.
So if you have a virtual double category that has loose identities and left composites, is this something weaker than a double category, or is it still?
Yeah, good question. I mean, presumably, yeah, it will be. Because, for example, in a double category, composites of loose cells are associative, right? At least that's what I think of them.
Right.
Left composites are not associative.
Okay.
So you would certainly get something a bit weaker. I'm not quite sure what the structure would be.
Yeah.
It was something like kind of skewed double category in some sense. But yeah, I don't really know.
Right. I mean, but when you're taking this class phi of loose morphisms, that will define presumably a sub virtual double category of the original one that you're working. I mean, you're just taking the
word, yes.
You're just restricting, but now you're asking for these to be closed on the left composite. So this,
yeah, that's true. That's true.
This would be an example of one of these things.
It would be an example of one of these structures. But yeah, I don't know what these structures are. So
yeah, okay, thank you. Are there any other questions for Dylan?
There's a question in the chat. Bryce, if you want to read it.
Yes. So Callum asks, is this work kind of a double categorical version of Street and Walter's Unita structures? I guess it generalizes it, is the question.
I don't remember off the top of my head the precise relationship with Unita structures, to be honest. Let me see. It is the case that if you fix a class of loose cells phi, these cocompletions will be a. If we fix the class of loose cells phi, then the presheaf objects will be a Unita structure, I believe. So in some sense, it kind of is a generalization of Unita structures. But yeah, off the top of my head, I don't know the precise relationship with Unita structures. Yeah, I'm not sure I can give a good answer to this question.
The person in the chat says very
there somewhere, but I don't know precisely how.
okay. I think that answers the question. Thank you. We have another question in the chat. Can you see the chat, Dylan?
Can try.
I'll read out the question anyway for the recording. The construction on page 25. Oh no. There was a question in the chat, but now, oh yes. The construction on page 25 of 5 from psi is analogy or generalization of saturation and enriched category theory. Is this correct? Have you found any way to check whether phi exists?
It should be maybe a bit more precise. So firstly, this really isn't an analogy to the usual thing for enriched categories, and I don't want to present this as kind of a generalization, although you can show that the construction for enriched categories works as a consequence of this, but I don't want to say it's precisely a generalization of the thing for enriched categories. At one point, I wanted to kind of generalize the thing for enriched categories directly to virtual equipment, but it doesn't quite work out very well. Because there's a really subtle issue, which is that when you do the thing for enriched categories, you have to talk about presheaves and not about distributors. And there's a very subtle difference that comes up because, so for example, ideally the kind of class of loose cells that you want to consider will be closed under restrictions on one side. You can kind of guarantee this by taking presheaves, but if you just say, for example, that I have some kind of class of loose cells that's closed under restrictions, and then I close under loose left composites, there's nothing guaranteed that guarantees these work well with the restrictions. So there are some kind of very subtle points that this is not that closing a class of presheaves under phi colimits is not quite the same as closing under left composites. So in fact, I don't really see how to generalize the construction for enriched categories precisely to virtual equipments. So you might ask, for example, if I say I just start with my psi and close under loose identities and under left composites, this thing usually will not match the thing that you use for enriched categories on the nodes. It will be slightly different. So yeah, sure, you can construct some class phi which does satisfy a bunch of these conditions, but in fact, it usually won't have a presheaf object, even in the case of enriched categories. So I really don't have a good way of proving, there exists some phi such that these conditions hold. I think for that, you really have to go in particular to enriched categories and then do some things involving enriched categories. So yeah, I hope that's some kind of answer to the question.
Okay, well, we might thank our speaker again for an excellent talk.